Hello, I'm James Ryan. I'm presenting today bypassing backdoor detection algorithms in deep learning, original paper by Tan and Chakri from the Computer Science Department at National University of Singapore. And I'm presenting this for EE5263 Data Science and Cybersecurity, the final project. Here's an overview of what I'm going to talk about. So I want to give a brief introduction. I want to talk about backdoor detection. I want to talk about avoiding backdoor detection with adversarial backdoor embedding attacks, and I want to talk evaluating that adversarial backdoor embedding, and then a conclusion. So an introduction. What is a backdoor? A backdoor is a malicious modification to an algorithm or deep learning model. How do backdoors get there? You can embed backdoors by modifying trained data, or you can embed backdoors by modifying the model parameters after it's been trained. For this attack, we'll consider backdoors embedded through training data. How do backdoors work? Backdoors work with an embedded trigger input. So over here on the right, you can see two street signs. I'm not sure what they mean, but the street sign on the right, that image has a small square of white pixels in the bottom right. So that is a backdoor trigger. A poisoned model will recognize that trigger and will act in some way that the attacker determines to be adversarial. Now, why do we care about backdoors in deep learning algorithms and deep learning models? Consider, for example, a model that performs facial recognition, such as that might be in Face ID on your iPhone. If that algorithm is backdoored, right, Face ID may perhaps be backdoored so that Tim Cook's face unlocks everyone's iPhone. I don't think anyone but Tim Cook would be okay with that. Maybe also consider autonomous vehicles, right? If a embedded backdoor on a street sign may convince an autonomous vehicle that a particular stop sign is actually a green light, and so it will proceed to drive through the stop sign irrespective of what's in the way. You may also consider embedded backdoor in a model used for disease classification. It would be quite bad if a particular person who had all the symptoms of the common cold was instead prescribed chemotherapy for cancer. So I think it's pretty clear that we should care quite a bit about backdoors embedded in machine learning algorithms. So now let's talk about the threat model we use here. So the threat model the authors assume is that an attacker has access to training data before the model is trained, knows that a detection algorithm is being used, but they don't actually care which algorithm. They also need to know the model architecture because they need to inspect the hidden layer outputs and what the model architecture actually thinks is happening with all of the inputs. So let's give a pseudo-formal definition of backdoors. So let's let the input space to a model be X. A model input is some element X in X that's associated with a label Y. A backdoor trigger is some property B over X such that B of X, i.e. an input containing the backdoor trigger, is classified as T, not Y, where T is some incorrect label that we, the attacker, choose. So now some stuff that's used for backdoor detection. It's reasonable to expect networks to classify backdoored inputs differently than non-backdoored inputs. That's actually the entire point of backdooring a network. So because we expect them to be classified differently, we also expect that their last level latent representations should differ significantly because they're classified quite differently, so we'd expect their latent representations to differ quite significantly. We will get the latent representation and all these defenses due by looking at the last hidden layer of the model because it represents the highest level features of the inputs, and so if the backdoor trigger we expect to be quite a high level feature, so that's probably where the trigger will be activated. So current backdoor detection techniques use this. They look for difference in the hidden layer activation. There are two main categories of detections. There's some that use latent representations, or one that uses a latent representation to prune neurons to remove the backdoor, while there are two others that use the latent representation to actually filter the data set. So the pruning neurons modifies the model, filtering training data set actually changes the data set used and then retrains the model on the cleaned data set. Neuron pruning So there's the paper details there. The way this works is we assume we have a small subset of training data that we know is clean, and that our backdoor trigger is a very small modification to those clean inputs. So what we'll do is for every input class, find the smallest modification that misclassifies all inputs in that class, and we'll get all of those small modifications for every class. If any of those modifications are abnormally small, they're probably the backdoor trigger. So what we'll do is we'll look and see what neurons are maximally activated by that modification and remove them, and then retrain and find and see again, and continue removing maximally activated neurons by the abnormally small modification until we don't see that behavior anymore. So now on to one of the dataset filtration methods. This is by spectral signatures. For this, we will train the network with a poisoned dataset, so we don't need to know which subset is cleaned, but we'll train the network on a poisoned dataset and record latent representations of all inputs, and then perform singular value decomposition on the covariance matrix of the latent representations, so we'll get an outlier score for every latent representation for every input. Then what we'll do is we'll look at inputs that are outliers and just remove them from our training data set and retrain. And that, in theory, would remove poisoned inputs from our data set. So now the second method does something similar but with a different process. So as before, we will train the network with a poisoned data set and record all the latent representations, and then perform dimensionality reduction by independent component analysis down to about 10 or 15 features, and use k-means clustering to separate into two clusters. This paper we'll talk about it in more detail, you can go read that, but a process called exclusionary reclassification is then used to determine which, if either, cluster contains poisoned data. So now we've got an overview of some backdoor detection algorithms. Let's talk about adversarial backdoor embedding, finally. So the basic idea is all of these algorithms rely on differences between latent representations for backdoored and non-backdoored inputs. So let's try and minimize that difference. The way we'll do that is we'll introduce a new modified loss function for our backdoored model. So when training the backdoored model, we'll actually use this modified loss function, consisting of our original loss function plus some penalty term that penalizes the model for difference in representation between differences in latent representations of triggered and non-triggered samples. So samples, we want the latent representations of samples with or without the backdoor to be quite similar. And this is a very general definition, so it's quite flexible. We can target this penalty at specific defenses, or we can actually have a generalized defense. So some more on that. So we can target it at a specific defense. Later on in this paper, we'll actually target it at Wang et al.'s neuron pruning defense, and we will quite handily beat it. The problem with that is the way that we will target it at the neuron pruning defense is that we will look at the neurons that are highly activated, that are removed by the neuron pruning defense, and then we will try and minimize the difference between backdoored and non-backdoored inputs on those neurons. So that's not really applicable to dataset filtration because dataset filtration doesn't remove any neurons. So what we'll also do is we have this architecture for a generalized adversarial embedding attack, and we'll show later that that's actually robust against all three defenses. Okay, so to empirically determine, to show that it's robust, we'll evaluate it on several different models. Here's the setup we're going to use. So we're going to use two different data sets, CFAR10 and GTSRB. Both are image data sets. We use two different models, DenseNet and VGG in the E configuration. Our backdoor will consist of a 4x4 block of white pixels and will infect 5% of the training data. We just arbitrarily decide here that all of our backdoor inputs should be classified as 2. And then or as class 2. We will also train a baseline model of every architecture without adversarial backdoor embedding here. Okay, now let's get to some results. So it actually turns out that neuron pruning doesn't really work on VGG with the GTSRB dataset and DenseNet for the CFAR10. So we're not going to consider those later. And it's just a note the authors had. It doesn't really work. You can see in this graph over here on the right that attack success rate falls off at about the same time as model accuracy, and model accuracy actually falls off worse. So pruning doesn't remove the attack success rate without significant losses in model accuracy. But what pruning does work on is, for example, the DenseNet model with the GTSRB dataset. So here you can see that neuron pruning is very effective, where the attack success rate drops to 0%, pruning about 40% of neurons with very minimal loss to model accuracy. So that's great. So neuron pruning works pretty well. Can we beat it with a target embedding attack? Yes, quite handily. So here's the results. Same model, same data set, but now with targeted adversarial embedding. So neuron pruning is actually no longer able to remove the backdoor at all. And now there's a much more drastic effect on model accuracy. So this shows you that the neuron pruning defense isn't able to distinguish between neurons activated by backdoored models and neurons by backdoored inputs and by non-backdoored inputs. It's kind of removing at random and just harming the model accuracy. So now we'll talk about dataset generalized adversarial embedding. So dataset filtration by spectral signature and dataset filtration by activation clustering are actually beaten after about 30 epochs of training, whereas neuron pruning was a bit more robust and required about 10,000 epochs of training to defeat, but it was still defeated. So here are the hyperparameters for the models when we are in the GAE attack, as well as in table 3, we can see the architecture used for the discriminator network. So the GAE model versus GAE versus neuron pruning. It's not as effective against neuron pruning as TAE. So in our generality, we do lose a bit of power against specific defenses. But even so, neuron pruning is only able to remove the backdoor once it reduces the model accuracy down to 20%. And for reference, this is a dataset, the CFAR 10 dataset with 10 classes. So 20% is only about 10% better than random guessing. And it's very, very much not effective at all. So GAE is still very effective here. Spectral signatures. So if you'll notice through this table here, spectral signatures are quite a good defense in this column here against the baseline models. But against adversarial embedding, it is a much different story here. So you can see the poisons dataset, the poisoned samples here in the dataset in the baseline model versus the poisoned samples left in the generalized adversarial embedding model. Spectral signatures is a much harder time distinguishing there. So how about against activation clustering? Activation clustering is actually very much unable to distinguish between latent representations of backdoored and non-backdoored inputs against GE, despite doing very, very well against the baseline. So as you can see here, against here, right, attack success baseline, only get about 1.9% attack success at best, whereas at best we're getting 96% attack success, and actually a little bit lower, 74% on the low end for attack success against adversarial embedding, but still much better than the 1.9% we had before. Okay, so now let's talk about GAE versus statistics in general. So remember the question we asked earlier is all of these rely on statistical distinguishments between the distributions of the latent representations. So here are some plots of the distributions with 2 of the independent components over on the right-hand side, and just with correlations with the top eigenvector on the left-hand side. And you can see that this top here is the baseline model. So the 2 independent components here actually very much give a distinction between the backdoored and non-backdoored inputs. Whereas over here, not really. You can see that the non-backdoored inputs look quite different from the backdoored inputs. But with generalized adversarial embedding, right, it's a much different story. So here, it's much, much, much harder to determine any at all difference between the backdoored and non-backdoored inputs. This implies that GAE will be robust in the future against any future models that try and look at statistical differences between latent representations of inputs. GAE should be a very effective attack against any such defense. Okay, so let's wrap everything up. So in conclusion, we have introduced adversarial backdoor embedding. This is a new backdoor attack. It hadn't really been talked about before this paper. It is customizable. You can target it against specific defenses or train a generalized version, and either way, you can be assured that it is a very effective model for embedding backdoors into deep learning networks.